Howdy. The purpose of this video is to review the different kinds of bonding that I can have in a solid. So why do I care about bonding in a solid? Well, let's think about a couple examples. Let's think about a steel, something that's very strong yet tough. Let's think about a ceramic, something that can be very hard, but is also pretty brittle. If I crack, it'll break easily. Finally, let's think about a plastic. These are usually pretty soft and have very low melting points. So the differences between these fundamental classes of materials is related back to the kind of bonding that exists between the atoms and molecules in those systems. So while bonding doesn't control all of the physical properties in materials, it does have a very strong effect on a lot of these properties. Okay, so let's jump right into some examples. First, we're going to talk about ionic bonding. Now, ionic bonding is something that occurs when we combine a very electronegative atom, something that wants to steal electrons, with a very electropositive atom, something that wants to give off electrons. So remember, electronegativity increases as I go to the right and as I go higher and higher up on the periodic table, while the electronegativity decreases and atoms become more electropositive as I go to the left and as I go to lower and lower rows. So these atoms want to give up electrons, they want to become cations. Electronegative atoms want to accept or become anions. So let's think about a couple examples. Let's say magnesium oxide and sodium chloride. These are two prototypical ionic solids. So magnesium oxide. Magnesium has the electronic structure of neon 3s2, while oxygen has the electronic structure of helium 2s2 2p4. Now, if you don't understand this or know how to get there, I'd recommend going back and reviewing the video on electronic filling rules. Okay, so magnesium would like to, remember, lowest energy state is usually given by full closed shells. So both of these atoms want to get to full closed shells. How would they do that? Magnesium would tend to do that by giving up its outermost 2 electrons. So magnesium will tend to adopt the magnesium 2+ cation state, and that has a common electronic structure to the noble gas neon. It has a totally closed 2 second shell. Oxygen, on the other hand, would like to accept 2 more electrons, and so it'll tend to adopt the oxygen 2- state, which also has the same electronic structure as the noble gas neon. A very similar thing would happen in the sodium chloride case, so you can work through this yourself. So what happens now? Well, now I have a positively charged cation. In this case, it has a 2+ charge, and a negatively charged anion. And I know that charged particles will tend to interact with each other. So the Coulombic potential, Q1, Q2, over 4 pi epsilon naught r. That's the energy potential between 2 charged particles. So if the particles have opposite charges, they'll tend to attract together. So again, an ionic solid is a collection of ions. They have largely given up or accepted more electrons to achieve more stable ground states. And then those particles are they're charged, and so there's some electrostatic interaction between the different charged particles. Ionic bonds tend to be very non-directional because, again, that Coulombic potential is a radial potential. It doesn't matter based on a particular orientation. So that's an example of an ionic solid. Next, let's think about metallic bonding. So metallic bonds would tend to be made by atoms that have partially filled electron orbitals interacting with other atoms with similar electronegativity. So we see metallic bonds in the alkali metals, in the alkaline earth metals, in the transition metals, and in the post-transition metals. So let's think about an example. Let's say sodium. So sodium adopts the electronic structure of neon, 3s1. So if I take a collection of sodium atoms and I bring them together, we know that they're attracted somehow. Sodium metal is a solid material. And what happens is that these atoms come together and they have a lower overall energy if these electrons delocalize and distribute themselves throughout the solid. And so the picture that's sometimes drawn of this would have solid sodium cores, and this outermost valence electron, 3s1, these electrons are given up and they're distributed throughout the solid. So sometimes this is referred to as a sea of electrons type of a model. And when those electrons are smeared out, distributed throughout the solid, the overall energy system of the state is lower. So I tend to see this bonding in atoms that have partially filled orbitals and don't have large electronegativity differences between them. So if I think about the counter case, what happens if I introduce some oxygen into that sodium system? Well, remember, oxygen has a strong electronegativity. It wants to grab some of these loose electrons. And in this case, oxygen would steal 2 electrons, sodium would give up their electron, and I would have an ionic solid that looks something like this, Na2O. So metallic bonding, I tend to see that between atoms that have very similar electronegativity. So I could have pure metals, so pure iron, pure nickel, pure cobalt, or I could have alloys. So I could have, for example, an iron-nickel alloy or a copper-gold alloy. The key attribute here is that they all have partially filled electronic orbitals and they have very, very similar electronegativity. If the electronegativity is too large, then I'm going to have an ionic solid. Okay, let's think about the covalent bonding case next. Now, covalent bonds are where we have atoms that share electrons in order to get a full closed shell. So these tend to be very strong bonds and very localized. So the prototypical covalent solids are given by group 4 materials or some combination of surrounding materials. So for example, boron nitride, carbon, aluminum nitride, silicon carbide. These are all covalently bonded solids. So let's think about the carbon case for a second. This is a nice prototypical example. Carbon has 4 electrons, so its structure is helium, 2s2, 2p2. And actually what we observe in the carbon case is that rather than stay separate as s and p orbitals, we have what's called hybridization between these s and p orbitals. So if I think about diamond, which is a pure carbon substance, the s and p orbitals all combine, and I would have carbon equals helium 2sp3. So all of those electrons are found in these hybrid sp3 orbitals. Now, I still want to get to a closed shell, and because a closed shell, in this case, has 8 electrons, and carbon has 4 electrons, if I share each of those orbitals with a surrounding carbon atom, I can get to my full closed shell. So carbon, bonding in the carbon, it tends to be, in diamond at least, it's tetrahedral. And each of these sp3 orbitals overlaps and is shared by a surrounding carbon, which has its own other orbitals. So what I get in a covalent bond, I have a very localized, a very directional bond. These electrons, because they're localized, they're not free to move around, but it's a very strong bond. And again, I tend to find covalent solids, the prototypical covalent solids are clustered around column 4. And that's just because these are the cases where I'm able to, by sharing neighboring orbitals, come up with full closed shells in all the cases. Now, I've described 3 different kinds of principal or primary bonding, but there's something that's important to remember. We have looked at these distinct end members, but there's blurring, right? So there's a range of behavior from purely covalent to purely metallic. One example would be if we go down the group 4 column. So carbon diamond is a purely covalent bond, or it's a very strong covalent bond. As I go to larger and larger shells, these orbitals become more and more smeared out, and the system behaves more and more metallically. So by the time I get to something like tin or something like lead, it behaves much more like a metallic bond. So I could see that if I look at the melting points of the different solids as I go down. Carbon has a melting point of 3,500. Silicon has a melting point of 1,400. Germanium 940. And tin of about 230. So the bonding energy decreases as I go down, and the electrons become more and more delocalized. So by the time I get to tin, those electrons are relatively able to move around, and I can transport current through the material. I could get gradations also between covalent and ionic solids. So if I think about something like sodium fluoride, that would be a very ionic solid. But as I move over, magnesium oxide, it's also very ionic, but a little bit more covalent. As I move over again, aluminum nitride, now I'm getting more and more covalent behavior, and silicon carbide has an even more covalent-like bond between it. So again, I'm moving this way with my cations and this way with my anions. I'm moving from things that have a very large difference in their electronegativity to things that have a much smaller difference in their electronegativity. So when I get to the silicon carbide case, those electrons tend to be shared rather than entirely stripped off and belonging to one atom rather than the other. So those are our kinds of primary bondings. The next kind of bonding that I need to think about is called secondary bonding. And so you can think of molecules. So for example, let's think about methane, CH4. So within this molecule, I have filled up all of my orbitals. So I have carbon, there's 4 hydrogens around here, 4 covalent bonds. Each hydrogen has 2 electrons, each carbon has 8 electrons. Everything has a closed shell and it's happy. So this likes to exist in its independent state. But if I start to bring a bunch of methanes together, they will interact with each other to some degree. And this kind of interaction is called secondary bonding. So in this case, it's I have 2 nonpolar molecules. And so what would happen is I would have an induced dipole in each molecule. So because neither of them has its own independent dipole, the electron clouds can start to fluctuate a little bit, and I can have a very weak sort of an induced dipole between the 2 molecules. If I look at the interaction between a nonpolar molecule and a polar molecule. So let's say something like water. Water, if you remember, has a bent structure. Oxygen is electronegative, so each of these tends to have a dipole, which means that there is a net dipole in the system. So there's a little bit more negative charge surrounding the oxygen, a little bit more positive charge down by the hydrogen side. So this molecule has a dipole. If it comes near something that's nonpolar, like methane, it can induce a dipole. So this is a case where I could have a dipole-non-dipole interaction. Again, these tend to be pretty weak. So finally, what if I consider the interactions between two polar molecules, so water to water, for example? In this case, they both have net dipoles, so there can be a little bit stronger interaction than in the previous cases, but still is relatively weak compared to primary bonding. So when you think about secondary bonding, this is also called van der Waals bonding. This is the sort of bonding that happens between molecules or atoms that are already electrostatically happy. They've already filled up all their shells, but there can still be some kind of interaction between these atoms or molecules. So I see secondary bonding within, for example, the noble gas atoms or between different molecules. One example would be between different polymer molecules. So I could have a long chain of polyethylene. So each of these is a carbon sitting here. And there's two hydrogens coming off each carbon. So that's one chain, and then I could have a neighboring chain. And there's some interaction between these two chains because we know polyethylene can form a solid material. And so the interactions between polymer chains is oftentimes caused by secondary bonding. So the final thing that I want to point, and I've already mentioned this a little bit, is the bonding energy in these different kinds of bonds. So if I think about ionic, covalent, and metallic, these all can have they can have a range of bonding energies, but they're all fairly large. So ionic tends to be from about 1500 to about 500. This is kilojoules per mole. Covalent tend to cover about the same range. Metallic can be a little bit less, so something like 1,000 to even as low as 50 kilojoules per mole. So those are primary bonds. Secondary bonds, on the other hand, are all much lower. The van der Waals, so typical secondary bonds can be on the order of about 10 to 40 kilojoules per mole. Hydrogen bonds, which are a special case of secondary bonds, tend to have a little bit higher energy levels. So these are about 20 to 50 kilojoules per mole. Okay, so as a review, there are a few different kinds of primary bonds. Covalent, these tend to be between materials that have very small differences in electronegativity, but can lead to closed atomic shells. Ionic, materials that have large differences in electronegativity, so they actually give up or accept electrons and be positive or negatively charged ions. And metallic bonding, so these are materials that have incomplete shells. They can't fill the shells, but they still achieve a lower energy state by delocalizing those electrons throughout the solid. Additionally, we have secondary or van der Waals bonds. This could be between induced dipoles, between two nonpolar molecules. This could be between a permanent dipole and an induced dipole, or between two molecules with permanent dipoles. Hydrogen bonding is a specific case because when there's a hydrogen atom and when it bonds to something like nitrogen or oxygen, it almost always leads to a very strong dipole in the system. So those can form a little bit stronger, but still much weaker than the primary bonding bond strengths. And finally, and this is important, remember bonding can be gradational. So I don't only have purely ionic and purely covalent. I could have a mixture between ionic and covalent bonds, between covalent and metallic, and between ionic and metallic bonds. Thanks.